Hello everyone, welcome to TechnoGate. So in the last class we have completed the power supply. So in the power supply we have started our discussion with the rectifier, then we have discussed the filter and how the xenodiode works, that we have also realized, and after that we have discussed the very important part of the power supply, that was regulator. So till the power supply completion we have completed the one phase of the application of the diode. So in the today's class onwards we are entering into the another phase of diode application. We are going to begin our discussion, that is with the clippers. So clipper is one of the very important application of the diode. After that we will also talk about the another very important application of the diode, which is clampers, and the smaller topic, that is multiplier. So one by one we are going to talk about each and every topic in the upcoming classes in the diode application section, of course. So let's begin today's class discussion with the clippers. So clippers, as its name suggests, clip something which is get removed or cut. A circuit which can remove or cut undesired portion of a waveform, or we say a circuit which can cut or remove unwanted portion of a waveform is called clipper. Basically, clippers are used to limit the amplitude of the waveform. Suppose the input waveform we have taken, that is varying between plus minus 12 volt. Suppose it is varying sinusoidally between plus minus 12 volt. Okay, and as per our circuit need, we are expecting the input has to be vary between plus minus 10 volt, or we want to vary the input like from 0 to 10 volt only. So for that kind of applications we utilize the circuit which can cut or remove the undesired portion of the waveform. And the meaning of undesired word is simply defines the need or application for which we are utilizing the clipper. Okay, so obviously we say undesired, which means for that particular application that particular section of the waveform is not required. Okay, so this is not a specific one, it's a general thing. So we will discuss so many types of popular clipper circuits. By name we say shunt clippers and series clipper. So under these two categories, one by one we will come across the so many sections in which waveform will be cut or removes in a different manner. Okay, so we focused on it. So it's a very simple topic and one interesting one as well. So let's begin our discussion with the definition. What I said, just write it down. What I said here, clipper is a circuit which can cut or remove undesired, or we say unwanted portion of the waveform. Undesired, or we say unwanted. That means we don't require that particular section for the given waveform. So we will simply remove or cut that undesired portion of the waveform. A circuit which can cut or remove the undesired portion of the waveform is called clipper. And of course clipper can basically make the waveform as an amplitude limited value. Suppose we have removed the certain section of the amplitude, so of course we say the clipper circuit is also called amplitude limiter waveform, or amplitude limiter circuit. You may also write in other words, a clipper circuit can limits the amplitude of the waveform hence clipper circuits are also called are also called amplitude limiter. Okay, so whether we use the word clipper, so it define itself. Okay, we are clipping, we are cutting something. Okay, and whether we use the word amplitude limiter, it is also defining itself, which means if we are making the amplitude is to be limited, which means we are cutting or removing some undesired part. So note this definition. Now let's consider the two major categories of the clippers. So we will discuss them one by one, of course. So let's make a heading here over here that clipper has two major categories. The clippers has two major categories. Basically, an element of the clipper which is responsible for the clipping action. And of course, we are using here the diode application. So of course, diode is the element which will be utilized for the clipping or cutting of the waveform. So in that circuit, we must say that diode, if the diode is connected in shunt with the output at which we are taking output, at the terminal which we are taking output, if the diode is connected in the shunt way, we say shunt clipper. If the diode is connected in the series with that, we say it is series clipper. Okay, so there are two categories, guys. The one is shunt clipper, one is shunt clipper, another is series clipper. The one is shunt clipper, another is series clipper. So if we say what is shunt clipper, we must say in the one line statement, if V0 is taken in shunt with the diode, that means V0 means what? The output voltage. Basically, we have applied some input waveform and we are generating the output waveform. Okay, and if this generated output waveform is taken in the shunt with diode, that means it is shunt clipper. So what we will say in the shunt clipper, V0 is taken in shunt with the diode, then we say it is shunt clipper. If the V0 is taken in the series with diode, then we say it is series clipper. V0 is taken in series with the diode, then it is called, guys, series clipper. Please note each and everything which I have written on the board. Shunt clipper is here and here it is a series clipper. So let's begin our discussion with the very first, that is shunt clipper. Guys, these categories are the very major categories. Okay, so in the shunt clipper or it is series clipper, you don't have the need for gate examination purpose. If I say very particularly, you don't have the need to remind your circuit as it is. Don't have the need. Just understand the operation of circuit, how the output waveform will be obtained for the given input waveform, okay, on the particular circuit, and how the diode will be behave in that section. So these things will be important for you, which means in one word I must say we have to approach clippers section qualitatively. We don't have the need to go into the quantitative approach where we have to remind circuits and all. We don't have the need to remind circuits, any of the circuits at all, for the gate examination point of view particularly. Okay, so let's come to the very first heading here, that is called shunt clipper. That is called shunt clipper. So of course, as I have already discussed the definition of it, now let me draw a circuit for you for the shunt clipper. Suppose this is the resistance R that we have connected over here, and the one diode I am connecting here. So guys, of course this is a shunt clipper, so output will be taken in the shunt with the diode, and here we have connected the reference voltage. Guys, please listen to me very carefully. The reference voltage basically defines the reference voltage, which I have denoted here by the VR. It is basically defining here the which reference value we are going to cut or remove the undesired portion of the waveform. Okay, so purpose of this VR is what? Which reference value we are going to cut or remove the waveform basically. Okay, so guys, Listen to me carefully. So this is the V naught at this node we are taking here, okay, and this is the node where I am applying the V input, okay. And the purpose behind connecting this resistance R T that R is to basically limit the current flowing through this diode, okay. What amount of current has to be flow through the diode? To limit that current, we have connected resistance R. So if anyone says to you, no one is going to say to us, but we must have to be this knowledge, this R is called current limiting resistor, okay. This is going to limit the current, so of course it is called current limiting resistor, and purpose is very clear about it, okay. Why we have connected this current limiting resistor? So that we can limit the current flowing through the diode. And what should be its value? Generally we say we don't require its discussion at all, but I'm telling you, generally we have required the value of R, that is under root of RF into RR, okay. This is the value of resistance R that we have basically required here. So RF defines the forward resistance of diode, which means whenever diode is in the forward bias, amount of resistance diode offered, okay. RR defines the reverse resistance of diode when the diode is in the reverse bias, the RR amount of resistance diode offers. Got it? It's a very simple philosophy. Now we see what is VR here, guys. VR is the reference voltage. VR is reference voltage. So in the entire discussion of clipper circuit, we consider any kind of clipper circuit, our complete discussion will be comes across with respect to input voltage, how the output waveform will be obtained, which means we have given the input waveform, and with respect to input waveform, how the output waveform will be obtained, the first thing that we will determine for every clipper circuit generally, okay. And the second thing that we will determine here is the transfer characteristics, which means with respect to variation in the output, how the output is getting changed, the relation between input voltage and output voltage with each other will defines by the transfer characteristics, okay. So two major things we will discuss for every clipper circuit generally, okay. So let's begin our discussion. Guys, this is the very first circuit, so that I'm considering here this diode is to be ideal, okay. When the diode will be practical, we will also discuss that thing, don't worry. So let's assume here what we are assuming here, diode is ideal. Diode is ideal. We know that one thing about the diode, if the diode is ideal, let me put something which is very important in the box. Ideal diode. When we consider the diode is to be ideal, so under the two situation, suppose if the diode is forward bias, it will be act like a short circuit element, okay. We also say, in other words, diode is in the on state, okay. When the diode is in the reverse bias, we say diode is in the off state. In that condition, guys, we consider the diode is as a open circuit element. Also, these are the predefined consideration for the ideal diode. Now let's take the input we have applied. Suppose, guys, if I'm considering the input waveform is of a very simple sinusoidal waveform, okay. So guys, don't we get scared. I am going to put input and output waveform on a single scale so that you will get a better clarity, okay. I can also put them on a different graphs, but here for your convenience purpose you will get it better, so that I am going to put input as well as output waveform on a same scale. So suppose this is the V input that we are applying over here is we have taken here. So suppose its value is varying between plus minus Vm. So guys, one DC voltage level that we have defined over here, that DC voltage level that we have taken, suppose I have denoted it by VR. So its value, either it could be positive or it could be negative. Of course it could be positive or negative, okay. So let's make the first a general discussion which will be applicable for all the situations. whether this VR is positive or it is negative. Let me see two cases. The case one, listen me very carefully. These discussion are very simple things, okay? So don't be scared of, just listen each and everything which I am saying carefully. So suppose we have taken the very first case over here. In the first case, suppose if I am taking, guys listen one thing, the VR is just a DC voltage. VR is what? DC voltage. So of course I'll say the VR value is constant always. Clear one thing? VR value is always constant, a DC level, okay? But V input is getting changed. So of course we are going to compare this V reference value with applied input voltage for sure, definitely. So I can make two cases. The first case I have taken here, if the V input, which is getting varied continuously, is suppose is greater than this V reference. I don't know whether this V reference is positive or negative, okay? But I know one thing here, that V input which I have taken is, the V input that I have taken is greater than V reference, okay? So if the V input is greater than V reference, so of course we will say the diode will be in the forward bias. Let me recall it for you. I know you all are very familiar with this thing. When P region has high, P at high, okay, N at low, diodes comes into the forward bias. So guys, if this V input node is at higher load, higher amount of voltage as compared to V reference, so of course we will say diode is in the forward bias. So guys, in this condition diode will be forward bias. That means I'll say this will be replaced by the short circuit. So our equivalent circuit will be written as like this. You may see our equivalent circuit will be written as like this. This is like that. Here V naught, okay, this is V reference. Now guys, tell me, if you are having basic knowledge of network theory, easily you may conclude one thing here, whatever the output voltage is just equal to this V reference. Am I right or not? Yes. Now guys, let's come to the second case where we are considering this V input is less than V reference. So guys, in this condition, of course, if this applied input Vi is less than this V reference, in this condition, can I say the P region is connected with the P side of the diode, okay, and N region is connected to the reference voltage. Some of you are getting confused. So this point may comes in your mind if you are initial phase of understanding. You can say there is a resistance. My dear, resistance can do anything only if current is going to flow, okay? Diode is just like a switch here. If the diode will not operate, current will not flow, diode will not come into the conduction, okay? So until unless current is started flowing, we consider this resistance R is to be just an ordinary element, and you may just assume this Vi is connected to this V diode directly, okay? You can understand in that way. Getting it, you will get it better if we are going to make some more discussion on it, okay? So let's come to the second case, guys. Let's come to the second case. In this case, I am considering the V input is less than V reference. This time if V input that we have applied is less than this V reference voltage, so of course guys, this time diode will be reverse bias. Getting it? Yes, diode will be reverse bias. So of course reverse bias diode will be act like a open circuit element. Diode is reverse bias, that will be act like a open circuit element. So guys, in this case our equivalent circuit will be represented like this. Here diode is open circuited, and here plus minus V reference is connected like this, and here plus minus V naught is to be connected, and here plus minus V input is to be connected, and here resistance R is present. Guys, resistance can do anything only if there is a current flow. Here we have termed this diode to be off, so of course there is no current flow, which means I can say whatever the V input voltage will be appear at the output terminal. So in this condition you can clearly say there will be no voltage drop across the resistance because there is no current flowing in this loop. So of course, in this particular case, guys, V input and V output will be equal. Okay, so these are the cases we have discussed. Please note each and everything which I have written on the board. First part I have taken where Vi is greater than V reference. Please note this down. Have you noted it? Now let's come to the second case where we have seen Vi is less than Vr. In this condition, output came V not equal to Vi. Now we will see the particular things. Maybe the V reference that we have taken as a positive or it is negative. But characteristics of the diode is not depends on that thing. Na? Characteristics of diode is depends on what? The difference voltage which is appearing across P to N region. So if the difference voltage from P to N is to be positive, that means diode will come into the conduction. It will be on state. If the difference voltage appearing between P to N is of negative, then of course diode will not be coming to the conduction. So please note the discussion which I have made over here. Have you noted this? Now let's come to the head. Now I am taking the two situations. The case one, if case one, instead of saying case one, if I'm saying if first part, if V reference is positive. Guys, listen very carefully. It's a very basic discussion, but if you get confused in it, then it may put bit troubles to you. Okay, so it's a very easy thing. You will get it in first time. Okay, suppose this is the input waveform which I have drawn over here. This is input waveform, and guys, we have taken the V references to be positive. Please don't judge this. Okay, this section seems to be high this as compared to this. Just assume each and every section is of plus minus Vm value. Okay, I'm sorry. So guys, these levels are plus minus Vm, plus minus Vm. Here I have drawn this input voltage waveform, and the V reference is positive, and V reference is what? Basically this is a DC voltage level. It's a fixed value. So if this V reference is positive, guys, I can simply mark this V reference over here because it's a DC level. By marking this V reference over that line, it will be easy to us to identify whether the applied input is less than this V reference or it is greater than that. So you can clearly observe from here what I am saying. See, under the condition, if I consider this section, that smaller section, let me zoom it for you. Okay, see, if I'm considering that section only, I can say V input is rising from 0, but it is less than Vr before that section. Okay, and from this part to that part, we are having V input greater than V reference. Am I right? Yes. From this part to that part, we are having V input less than V reference. Got it? Now we have already observed the characteristics. What will happen if V input is greater than Vr? Output will comes is equal to Vr, which means under this section from that node to this node, output waveform, I am just overlapping that waveform by the output waveform. Guys, please be careful. What I am trying to convey to you, see, this is the overlapped region which is defining the output waveform. It will be easy to us for identify it. Okay, I'll also draw it separately if you are expecting it. If the V input is less than Vr, which means that section to that section and this particular one. So in this condition, output and input will be overlapped like this. Okay, so input and output waveform will follow each other. If you want to clearly understand this section, have you noted this waveform? This was the exact waveform of input. Okay, and with respect to this input waveform, our output waveform will come like that. For the input Vi greater than V reference, output V naught is equal to V reference. For the input Vi less than V reference, output came V naught equal to Vi. So guys, this is the output waveform that will be obtained over the input waveform. Okay, I'm just showing it by the dotted line, the input waveform like this. Okay, this is the input waveform which is complete one, but output waveform came clipped. So what we have seen over here, we have seen here the input waveform is clipped above the reference voltage. Whatever the value of input voltage above the reference, it is simply get clipped over here. Okay, this is the simple thing that we have observed. Suppose if I'm considering the second case where you may write out it over here. So if I'm considering the second case, guys, where I'm considering the input, sorry, not input, it's second case where I'm considering this V reference is to be negative. Okay, so guys, our input waveform is of, this is our input waveform. Okay, and V reference will be somewhere here. It is negative, so of course it will be somewhere here. But the ultimate observation of circuit will not affected by this. Vi greater than Vr means V not equal to Vr. Vi less than Vr means V not is equal to Vi. Which means for the part of the waveform where V input, this is the V reference, okay. V input is greater than Vr. In this condition, V naught is equal to Vr, which means our output waveform will be of like this for this waveform. Okay, and for V input less than Vr, we simply take the output waveform that will be equal to Vi. So guys, in this condition, the output waveform that we have obtained over here is simply V naught equal to Vi. Okay, so let's draw this waveform. Guys, don't get confused. Let me draw it separately for you. If you guys are getting confused, let me draw it separately for you also. See, this type of output waveform will be obtained to us. What we have clipped over here, is the upper part of the waveform above the reference. So this particular clipper circuit which we have drawn over here is also called clipping above reference circuit, because this is the VR which we have defined as a reference. Please note each and everything which I have written on the board. Please note this down. Noted this one. Okay, done. Now we have defined a reference voltage, and the output which we have generated over here is simply the clipped waveform which is clipped above the reference level. Okay, so whatever the value of input is above the V reference DC label, simply it removed by the clipper. Okay, so the value of voltage which we are having with is of varying like this. Suppose if the V reference is of negative, then of course this section will be left with us as an output voltage. If we are having the reference voltage is of positive value, then of course this section will be left with us as a final output voltage, this which is denoted by the red ink. You can clearly observe it. Okay, further you may also write. So this will be our final waveform that we are obtaining over here. Have we noted this? Now let's come. This is the output waveform we have seen, and as I already told you, we are also having the one more section, that is transfer characteristics. Let's come to the transfer characteristics. For of course for this V reference positive, and for also negative. Let me draw. So before drawing transfer characteristics, let's write a brief definition of it. Let's make a heading here first. Transfer characteristics. Transfer characteristics. ये क्या लिखा? Characteristics. Okay. Transfer characteristics. So when we consider the transfer characteristics, so it's simply a variation of output voltage with respect to variation in the input voltage. Basically, we know the input is varying sinusoidally or maybe by any other kind of function. So with respect to change in the input value, how the output is going to respond on it. So this plot is basically defines the transfer characteristics. So you may note this one point over here. The variation of output with respect to variation in the input is defines in the transfer characteristics. In the bracket you may also write the plot between V0 versus Vi is called transfer characteristics. It's nothing how input how with respect to variation in input output is going to change. This is simple transfer characteristics. Let me draw it for you, then it will be completely clear to all of you. So here in the first case that we have considered, if the V reference is to be positive, so the vertical axis guys I am taking here for the voltage axis, okay, as usual we consider in that way, and the horizontal axis which I am taking over here is as a input voltage. Okay, so of course this section is defining the positive input voltage range, and that section is defining the negative input voltage range, and this section above this center is defining the positive output voltage range, and that section below this center value is defining the negative voltage output range. Okay, so if it defines the reference is of positive, then of course I will mark the points. Okay, suppose on the output axis as well as on the input axis I have marked points. Suppose I have marked over here plus VR here, because reference is positive, so that I am just marking them. And guys, this will be the intersection point where V0 and Vi will be both is equal to VR. Now let's come to the analysis which we have done here. What was the analysis? Sometimes they also simply ask the transfer characteristics. So in that scenario, we don't have the need to draw the output waveform. We will simply realize how the diode is operating, how the output voltage is getting generating, and simply on that basis we will simply draw the transfer characteristics. It's a very first question, so that it's a very first analysis of the circuit, so that I'm going to deal each and everything in the very slow motion. Maybe you are feeling that, but it's absolutely fine if you are getting each and everything of mine what I'm saying. Okay, so my purpose behind the entire discussion is only one. I want to make you strong conceptually. Okay, so be focused on each and everything. I'm discussing each and everything in the from basic to the advanced level. Don't worry. Okay, so Vi is less than V reference, which means our input is less than V reference. In that condition, output is just following the input. That means V0 will be what? Whatever the Vi. Okay, if any point of time input voltage is of any value, suppose it is 0, then output will also be 0. V0 equal to Vi. Got it? And if input is of negative, then output also must be negative. Whatever. Vi less than V reference, this is the scenario, and for Vi greater than V reference, output is equal to V reference. Let me draw it for you. So for the input V0 less than V reference, exactly this kind of a straight line graph will be obtained. You may also say the graph is of showing here V0 equal to Vi here. Once we reaches the V reference level of the input voltage, then of course our graph becomes like this. So this is the section where output voltage becomes V reference. You may clearly understand here input is getting increased in this entire line for a greater value than VR. We are saying simply input is getting increased here, but output remains constant at the VR value. So this is the transfer characteristics under the case where we have taken the V references to be positive. So guys, once we have understand the approach, then of course, even if the V reference is to be taken negative, the fundamental will not be modified. No, the fundamental has to be remain same. Okay, let me draw it. Let's draw it first. Noted this. Now let's come to the second transfer characteristics, guys, where we have taken the V reference is to be negative. If the V reference is to be negative, then of course I'm not defining this is the value of V reference. I'm defining the DC label, because V reference is, even after V reference is what? It's a DC label. So let's see. This is the DC label which I am defining. Suppose this is minus VR, and here also it is minus VR. These two DC labels we have defined here. Okay. Now, before V reference, V input less than V reference, output came V0 equal to Vi, which means in that section I can clearly say this output will follows the input, which means for this section particularly I'll say this V naught is equal to Vi. Once input will reach to the V reference level, then of course our output will becomes a constant at V reference. So in this condition, simply our output becomes minus V reference. Whatever its value, its numerical value is not the challenge. The thing is how the circuit is actually behaving like. Have we noted this discussion? Please note this discussion for the V reference negative also. Okay. So in this class, we have started our discussion with the shunt clipper. In the shunt clipper, we have seen, have we noted each and everything? Let me scroll it again for you. Please, first of all, note this discussion entirely, which I have written on this. Okay, then note this down. Now note this down here further, and this transfer characteristics also. I have represented everything on the screen. Okay, please note it now. Come to a very important point. In this circuit analysis, guys, we have considered the diode is to be ideal. Okay, that may considered in the paper also. But sometime in the exam, they may also utilize a diode which is practical diode. So no issue with this thing as well. We have also discussed the practical diode, but let me recall practical diode philosophy with you. So when we consider the clipper circuit, in the clipper circuit, our output voltage or input voltage is of varying under the range of few volts. That could be varying between plus minus 20 volt. That may be varying between plus minus 15 volt. So it is of range of few volts. So we will replace here diode with a non-linear model. Basically, we will replace diode with a ideal diode plus V gamma battery. So write a node point over here. If we consider, write a node point here. That node point will give the clarity to you, and by solving numericals you will become comfortable with this analysis. Okay, so let's write a node point over here. What was that node point? If in the given clipper circuit non-ideal diode is given. Non-ideal diode is given. Then we can realize such clipper circuits. As follows. See, suppose about the terminal A and B, this is suppose terminal A, this is terminal B, and they have given a diode to you like this about terminal A and B. They have given, this is the non-ideal diode, guys. What they have given, this is a non-ideal diode. So we know that the practical diode will come into the conduction even if the forward bias is applied, only if the applied input will crosses the cut-in voltage, which means it will not come into the conduction unless the applied voltage crosses the cut-in voltage level. We know that thing. Okay, but if we say the ideal diode, that ideal diode will come into the conduction even if the applied voltage is less than cut-in voltage, just it crosses the positive value, the ideal diode will come into the conduction. But this thing is not happened with the practical diode. The practical diode has significant cut-in amount of voltage required. So while using this non-ideal diode in the clipper circuit, we must have to utilize it in this way. See, I have replaced it with the ideal diode here. This is ideal diode. Okay, along with a plus minus V gamma supply. Guys, don't get confused with the polarity. Please don't get confused. I have written it absolutely right. Okay, you may also understand in that way. Suppose you have noted this, please note this down. Noted. Now sometime they may also give circuit to you in this way. I'll also write for you in this way. Okay, if the circuit is given like that, and if the circuit is given like that, okay. So please come. So see, A and B is here. Here I have taken the non-ideal diode. Here I have taken a non-ideal diode, and now I am going to replace it with the equivalent model. Once they have given non-ideal diode to you, just replace that non-ideal diode in this way. Ideal diode and this V gamma battery. Got it? So it will be easier for you to replace this V gamma battery, to replace this non-ideal diode by this circuit. Now entire analysis will be same as I have just made for you. Okay, so there will be nothing different. Simply the difference was made by the non-ideal, which we have resolved here. Simply consider it with the V gamma battery and ideal diode. Okay, for any of the circuit, just remove it from there and just put that diode over here. You will be able to answer it. Okay, now here in that way, if the circuit is provided to you, then we will simply replace it in this way. Here I'll draw it as an ideal diode first. What we will do here, we'll draw it first as an ideal diode like this. Got it? Now we will connect a simple V gamma voltage battery, plus minus V gamma, along with it. So now we are able to find exact analysis. So these two things we must have to be take care of. Okay, the first thing, actually there is no difference between that circuit and this circuit. Okay, but sometimes we may also get confused while facing all these things in the exam. So if they have written diode like this, you may simply replace in that way. If they have written diode like from down to up, so you may simply draw it in this way, because both are the identical thing actually. You can clearly understand it. Let me give you a proper approach behind this discussion. Let me give you. So if we realize it, you see here we have taken the A terminal is connected to the N side and B is to the positive P side. So of course the supply came here, N side negative, P side positive. Got it? And you can say here P side is connected with A, N side is connected with B, supply here again P side with positive, N side with negative. Got it? So of course V gamma will be in the direction of plus to minus. So of course this PN junction voltage, when it will be in the forward bias, this PN junction voltage will appear in this side, plus minus. So here I have replaced plus minus. So don't get confused. Simply while solving the clipper circuit, just replace that section by this way, that section by this way. Now I'm giving you one question. I'll give you the hint in this class, okay, but I'll not discuss its entire concept in the today's class. I'll discuss just hint, okay, because I have given you the concept. Just I have discussed that shunt clipper circuit. So in the today's class, I'll discuss the hint about it, and I'm going to put that question as a homework for you, and it's your responsibility to answer it entirely. Okay, so see this question. I'm going to read this question for you. In the circuit shown in figure, diode has cut-in voltage 0.7 volt. 0.7 volt cut-in voltage they have provided, and input is 10 sine omega naught t. If you are getting confused with this, what they have written, I'm writing it properly for you. V input they have given, guys, 10 sine omega naught t. Okay. Plot the output waveform and transfer characteristics. They are asking for output waveform and transfer characteristics. I have discussed the same circuit just before, but this time this circuit is given as a numerical data for you, and they have used the practical diode, guys. Okay, so how the practical diode is different from the ideal diode, that I have also provided this knowledge to you. How this practical diode is different than the ideal diode, that we have seen. Okay, so just remove that diode which is connected over here. Just remove that diode, suppose by taking it as a terminal A, taking it as a terminal B. Remove this practical diode over here and simply replace it with the diode which is ideal and the V gamma battery. You will have the complete analysis. So this time I am expecting its exact analysis from your side. Okay, so this thing will be as a homework for you. So that will be enough for the today's class. We will make the further discussion in the next class. Thank you.